because yours.
This is plotted.
Good. Everybody's going to want to watch this, right? 10 minutes of. Okay. Well, I am going to talk about basically how can you massage high frequency microwaves, meaning hundreds of gigahertz, and low frequency terahertz waves. That's the message here. How can you alter them? How can you get them to reflect? How can you massage them and make signal processing? But before we get to that, I thought I'd give you an inducement to come to Colorado Springs sometime. This is what it looks like from the campus. If you see these little red rocks over there, first day on that campus, they said to me, "See those little red rocks?" And I said, "Yes." And then they said, "That costs you $10,000 a year in salary because people want to live there." And so those are the little red rocks, and that's what it looks like when you're up close. And you can see it is really quite beautiful. And it's true, that costs you about $10,000 in salary. I noticed there was some difference, some actual, besides this fact that we speak nearly the same language, between Australia and Colorado. And in Australia, everybody lives within about, 50 kilometers of the coast. And in Colorado, everybody lives within, down this line. And if you're wondering what that line is, that's basically where the Rocky Mountains are. And so it's the same lifestyle. You basically only go north and south or east and west, depending on where, where you live. So it's actually very similar here. We have those mountains though, so you always know which way, in our case, which way west is. Okay, I'd hope this is going to be interactive. I'm happy if you guys want to ask a lot of questions. So please don't be afraid to ask questions. Just say, "Hey, what are you stupid thing doing right now?" Right? If you're confused. So I want to start with something that's where we're going. But I want to start with something that isn't quite about terahertz or high gigahertz range. I want to start with a really simple example of doing something that you don't really expect that is contrary to your kind of classical opinion of things. And it is going to be about ultra thin anti-reflection coatings. We all know, if you imagine that you have a substrate and then a dielectric on top, and you ask, how can I make this an anti-reflection coating, which works great in all of your glasses and so on? Pretty much everybody knows how to do this. You can do the relatively simple calculation and get the basically a destructive interference between the top reflection and the one from the second layer down. And it's always use a quarter wave plate. That's the rule. You can make it more complicated by including more reflections from top and bottom. It's still use a quarter wave plate, right? But it turns out that's when you're limited to basically pure dielectrics. If you use a non-lossy material, quarter wave plate is the right solution. If you use a material that has some loss in it, meaning has a fairly substantial imaginary part, you can still get a complete cancellation, but this is the imaginary part of the reflectivity, the real part. So this thing which is that one there, has to be balanced by all of those, and you can still do it, but now you don't have the quarter wave plate restriction. And so here's a result, and this is on vanadium dioxide. And what we're doing is plotting, it's a material that changes its dielectric constant with temperature. And so this color map is telling you how much is reflected. And you can see here at 342, you're at the bottom. And at 342, you have an epsilon of 6.75 plus 13.5 I. And basically, you can see up there that the film thickness that you would need for a quarter wave plate is 980 nanometers. But the actual film thickness that you can use to get to almost no reflection is only 180. So you're improving your quarter wave plate by a factor of 4 by doing something outside the standard. And my message here is you can get interesting things to happen by doing something different. In this case, changing the real and imaginary parts to be more equal. Okay, we'll do some of that as well, play off this real and imaginary. But now I want to talk about this non-reciprocal reflection in magnetic materials. So what do I mean by non-reciprocal? I mean basically that if you reverse the propagation, instead of going this way, you just go this way in some sense. Instead of that, if you reverse the propagation, something has to change. The frequency could change, meaning waves going this way have one frequency, but going this way have a different frequency, or the reflectivity could change. We'll see other things happen as well. Okay, and obviously this has some applications. The most immediate application is you can make what's called an isolator. An isolator would be something which allows waves to go one way, but not allows waves to go another way. So imagine you had an antenna over here and you want to send waves out on your antenna. Great, this is the way to go. But you don't want, for instance, an enemy to send a gigantic signal back to your antenna and blow up all your electronics. And so that's why you want the not allowed the other way. And this is used standardly on many systems for exactly that reason. The other thing you can do with this so-called non-reciprocal scheme is you can make what's called a circulator. And a circulator has a sense of rotation here, so that if you have a transmitter here, it goes to the antenna and out on the antenna, but it does not go over here to the receiver. If you come in on the antenna, it goes to the receiver, but it does not go to the transmitter. And so all of these things come from this non-reciprocal, one way is not the same as the other way effect. Okay? And what we want to see is how does that work in the high microwave and high gigahertz region and low terahertz region. That's what we want to talk about. Okay, in magnetic materials, all of these interesting effects come from the precession of the magnetic moments that they do in a microwave field, in an oscillating field. The magnetic moments go around like this, and it has a handedness. It only goes the way I drew it. It never reverses the other way. And that's what gives you fundamentally all of these, the sense of one direction. It's governed by this really simple equation. There's an effective field acting on this magnetic moment. This simple equation is really a standard equation you would learn in first semester physics. The change in angular momentum is the torque. When you're changing the direction of the magnetic moment, you're changing the angular momentum, and the torque on a magnetic moment is basically m cross h. So you have something really simple, and the frequency at which this thing goes around is basically, it's more complicated, but basically proportional to the effective field. So you can have this at different frequencies depending on what's creating your field. Okay, so this is where the handedness comes from, and the sense of direction comes from, is this sense of precession that only goes one way. Mathematically, that precession leads to a tensor permeability, not a scalar permeability, and it has a nice resonance, right? Where that frequency, that natural frequency lies. You can adjust the resonance frequency, for instance, by changing the magnetic field. And here is the diagonal components of the permeability with its perfect resonance. Great. But and as we often know, something good or something interesting at least happens near resonance. But there are also these off-diagonal components. And mathematically, these guys, the off-diagonal components, are the things that control that non-reciprocal behavior. Without them, you do not get a non-reciprocal behavior, as it says there. And what's interesting here is, remember the other frequencies, they were down in the 25 and 30 gigahertz range. If you look here at up to 300 gigahertz, this is that off-diagonal component if we're looking at iron, and you can see it's still well away from zero. So this offers you the opportunity of having this non-reciprocity, not only near resonance, but way up to maybe 300 or so gigahertz, maybe even higher. Okay, so not zero even at 300 gigahertz. This is again measured for iron as our base material. So we could look at where is our resonance frequency for different materials. Iron 10 to 30 gigahertz, hexagonal ferrites, they have a big anisotropy field, so it's higher frequency. And the first thing I want to talk about in more detail is antiferromagnets, where it's an exchange field, which is very large, and that gets you into the 1 to 2 terahertz range. Okay. So I'm going to talk at times about surface waves. I wanted to give you a picture of it. So imagine these are all precessing spins, and a surface wave means it's going to be larger at the surface and get weaker and weaker as it progresses into the material. And these surface waves often have also a one-handedness property that goes with all these others. So I'm going to imagine I just draw the surface wave. So this is like a zero line, and the surface wave has its biggest amplitude near the surface. Great. Where's the one-handedness come in? It's here. If you have a surface wave in a film, when it goes from left to right, left to right, it's localized at the top. When it goes right to left, it's localized at the bottom. So it'll go both ways. Technically, it is reciprocal. The frequency is the same, but the localization is different. And again, you can imagine this plays a role in what happens. So that just says what I just said to you. The localization depends on which way it's going. Oh, if you like some mathematics, I put this up here so people know there is mathematics behind it. If any of you are familiar with some people are theorists and some people are probably experimentalists. So let me get a sense of the room here. Anybody a theorist other than me? Okay, good. You all know Maxwell's equations. You all know there's probably magnetostatic form. You can look for surface modes. Here's the fact that it is localized, e to the minus alpha y. It's localized at a top surface or a bottom surface. You have boundary conditions, and you can do the dispersion relation. If you're interested, I can talk more about it, but I think for the general audience, nobody wants to see an hour and a half of long calculations. I know I never do. Did you want to ask? Do you want an hour and a half of? Yeah. Yeah.
Is important, and so this equipment
yeah, this equation is only for a particular direction, as it turns out. If you are more careful, you would end up with a couple of mu's. You would have both. I take it back. What I said is here, there is only one mu. When you get to the boundary conditions, it turns out the other mu shows up. It is in the boundary conditions where the other mu shows up.
But do I understand well that to get this
One way.
surface? Okay, no, the extent of the surface
right
is not related with mu xy.
It is related with mu xy. It shows up in step 3 when you do the mu xy shows up in step 3 there. Yeah. Okay, thank you. And I appreciate you breaking the ice so that everybody else will now ask questions. Especially the theorists in the back that usually sit silently. Okay, there are, as we saw, there are interesting things that if I imagine kind of putting a microwave current here to generate this surface wave, well, what do you think it's going to do? It's going to travel this way and then try and make its way around the corner, but it's going to lose energy as it does that. So I'm imagining there's a microwave field there generating the wave, and the wave is going to go this way. And actually, if you look at that, it turns out that this side just gets hotter because all the energy is dissipated over there. Of course, after time, it will spread out, no question. But initially, that side will simply get hotter, which is not something you normally expect. Okay, I want to talk about now a diode for electromagnetic waves. This is the reflectivity. So imagine I have my incident wave here, my reflected wave there, and this could work in my imagination. I will get a nice reflected signal. But what if I reverse it and have the incident wave here and the reflected wave there? And I am going to claim, and indeed show you some experimental results, where that does not work. And it comes from this sense of rotation. Okay, as I say here, it's not quite that simple. You have to make it a little bit more complicated. You need a magnetic field, the way I've drawn it here. You need a magnetic material, because this is all magnetic. And you need the right polarization. And basically, it's this polarization for your incident wave. But if you do that with an antiferromagnet, you get something that gives you this really quite strong one-way reflectivity. And we're going to look at the reference frequency region of 1.5 to 1.5, 4 gigahertz, terahertz. And that will be, this geometry will be called the forward direction. If we go the other way, amazingly enough, we're going to call it the reverse direction. Okay, the resonance frequency, if you have no magnetic field, remember I said you do need, in this case, a field, is 1.52. And here is, I know these numbers here are really small, so I have to write them big for you. Here's the reflectivity here. This is no reflectivity. Here's 75% reflectivity. Here is frequency, 1.5 to 1.54. And again, with no magnetic field, you get a nice signature of a resonance in the reflectivity, meaning a lot of reflectivity at this frequency and relatively little there. Great, now I'm going to turn on the magnetic field and show you something different. What happens is that nice single peak splits into two, one that moves up slightly, one that moves down. And you see this thing that says SR, surface resonance. So that surface mode is kind of causing a fairly substantial dip over here. This is 0.3 of a Tesla. And this is the, I think, the forward direction. There's the forward direction. And now the question is, what do I get when I reverse the incident and reflected waves? Will it look the same or not? Obviously, it looks different because otherwise I wouldn't be going through this. Here is the reverse direction. And you can see there's a substantial difference in the reflectivity between these two. And just to point out the most obvious region, here in the reverse direction, there's a dip, meaning almost no reflectivity. And in the forward direction, you're very close to a peak, meaning almost complete reflectivity. So you have made what you wanted, a kind of a one-way reflecting mirror. You can do a little bit better if you do what's called attenuated total reflection. You basically have a prism, you bring light in. There's, of course, it's a high index prism, so there's a critical angle when you go from a prism to maybe air or some other low index material. Beyond that critical angle, everything is reflected, but there is still an evanescent wave here that normally will not actually carry any energy away. So normally this reflected wave is quite large, but if this evanescent wave couples to our surface wave in there, it can take energy away. And so what you then get is maybe a slightly more sensitive scheme where the reflected wave really sees the surface waves. If you do that, again, here's forward, here's reverse. You can see they really look quite different in this case. And those are the surface mode regions here, and you can see they are physically located at different frequencies. And again, if we put a line through, you see one is very much at a dip, one is very much at a peak, and the reflectivity is quite substantially different. In one case, it's 0.8, and in one case, it's 0.1. So you really have something that is a non-reciprocal scheme at terahertz frequencies. Okay. All right. If you, again, for the theory people, just to show you there's nothing special, I don't know, maybe that's the wrong word because we like things that are special, but Maxwell's equations are used. You have to use both the epsilon and the mu with all the components. You look for wave-like solutions in each region. You match the solutions with the boundary conditions, tangential E, tangential H. Here is again where the mu comes in, and you get the reflectivity, just so that you have a feeling for how it's done. I want to talk now a little bit about other ways of doing the same kind of thing. And one way is to build a nanostructure. And the nanostructure gives you the chance to modify not only the magnetic properties, but the dielectric properties. The epsilon can be changed as well, and that can be quite helpful. The reason why you would do this is that a lot of ferromagnets like iron, nickel, and cobalt, they're metallic. And metallic materials, they just reflect everything up to visible, right? They really don't care. And so what we don't want to work with if we're trying to get high frequency reflectivity is you don't really want metallic elements, you want something else because they would just normally reflect the microwaves and you can't probe anything or use them. So what we're going to do is we're going to make a new kind of material, a metal insulator structure, and we're going to use effective medium to calculate it. I'm just going to give you a hint about it. What do you need to use effective medium? You need the wavelength should be bigger than your microstructure that I'm building in. Just to give you some numbers, the wavelengths, we're talking about millimeter waves. So 1 millimeter to 1 centimeter. And the structure size we'll think about as 1,000 nanometers or smaller, no problem there. Here's the idea. Suppose you have metal, insulator, metal, and so on. You can calculate the fraction of the material that's metal, the fraction that's insulator. And if you remember your physics 2, second semester physics, if this looks like a series of capacitors, actually. And the rule for the effective dielectric constant very much looks like the rules for capacitors in series. It's the fraction of the material with epsilon 1, this would be that material, and the fraction of the material with epsilon 2, but it's 1 over all the place. And what that does, to put this back up here, remember the metal has basically got a giant epsilon and imaginary. So if I imagine 1 over this, it almost drops out completely. And so what you've done is you've gotten rid of that metallic reflectivity by doing this. And to give you some just simple calculations, here's my fraction of the metal, here's my fraction that's dielectric, and you can see this is my epsilon effective. And what's nice about it is, hey, look, I managed to make the real and imaginary kind of on the same order. Remember our very first example. Now let's see what it does. So before we actually do this, this is the picture I made for you, but really we're not going to use it in this configuration. We're going to rotate this thing, then we're going to shrink it down, then we're going to extend it out, then we're going to put it in another material. Okay, this is my best, dynamic slide ever. So I just want you to appreciate the effort that went into this. And then the reflectivity will be basically coming in and out like that. Everybody understand the picture now? And basically what happens is, if you imagine this is a metal and this is an insulator, you want to get rid of the eddy currents that are going in there that make that metallic response. And by cutting it, you get rid of the eddy currents. Okay, that's the entire idea. So we got the idea that interesting things happen when you make the real and imaginary parts close to each other. And you have the idea that we can now do that, right, by making a microstructure of some kind. Our first microstructure is going to be magnetic nanoparticles. We're going to imagine putting tiny little particles, metallic magnetic particles, in a plastic or something like that. We're going to look at incident and reflected waves, just like usual. And first, we're going to look at the pure metal. So this is reflectivity, how much is reflected as a function of frequency. And this is the pure metal, and you can see it's always near 1. It's always nearly completely reflected. Now I'm going to put in my metallic nanoparticles, separated so I get rid of the eddy currents. And the first thing you notice is it goes from 1, meaning all the way down to 0. So I've now got not just a metal, I've got a quasi-dielectric material. And I also get some difference between the forward and reverse waves, right? Reflectivity is different. Still not that interesting because way up here at 100 gigahertz or so, not that much of a difference. So let me do one more thing. I'll put a dielectric overlayer on top. And now you can see I get over here at 80 gigahertz, which is pretty good. I get on the forward, it's about 70, 80% reflected. And in the reverse, it's almost nothing is reflected. So I now have something that I've made, a non-natural material, but it's used all the ideas that we've seen before that will give me, again, a chance to massage these waves about how they behave in interacting with materials. Okay, that's with magnetic particles. How about a real structured material? Going back to the thing we had before. So imagine I have this material with metals and a gap. I could put in some insulator in the gap. Okay, we've been through all of these things. We've talked about non-reciprocity in terms of the frequency is different. The localization is different. We've talked about that. And the reflectivity is different. And that's what we're going to look at now is the reflectivity again. What do we need typically? We needed all sorts of things. We wanted typically a resonance. We wanted surface waves. We were using the magnetostatic approximation, moderately thin, thick film and magnetic field. And what I'm going to say now is what I hinted at earlier. We don't really need that resonance. We don't need to be down in the 20 gigahertz range. We don't need the magnetic resonance because that will let us move away from this 10 to 25 to 35, 55 gigahertz range. Let us move up to 300 gigahertz. So we really want to be up higher. So this is our picture. Again, we're going to get rid of the eddy currents and we're going to use a metal because it has a large saturation magnetization, which gives us big off diagonal components. Okay, we're going to do this attenuated total reflection scheme. Again, that turns out to couple really well to surface waves, and that helps us out. And here, I'm going to spend a little bit of time on the picture of what we get. This is basically the the color is how much is reflected. I'll put up a color bar in a minute, but blue means mostly transmitted, red means mostly reflected. And what I'm plotting here is the angle of incidence, so negative angles over here, positive angles here. And here I'm scanning over all the frequencies from 0 to 300 gigahertz, 350 gigahertz. So the colors tell you about the reflection, and the horizontal axis tells you about where you are. So at this angle, incident, that's the scan you're doing, right over on that white line on that's where you are at all the different frequencies. If I change this angle here, it moves over there into the region where it's all basically transmitted. Or if I'm on the other side, it moves over there. So I'm hoping everybody has a feeling for this complicated color map because this looks really simple. Life is going to look much more complicated in a minute. Okay, so to come back, blue, again, I will put up a color bar, but I couldn't fit it in here. Blue means mostly mostly transmitted, mostly not very little reflection. This is mostly reflected. Now, if I add in damping and it's non-magnetic, I suddenly get all sorts of other stuff, right? Blue, mostly not reflected. Red means mostly reflected. And what are these guys? Those guys turn out to be coupling to electromagnetic surface waves, bound states. So you can see blue, again, mostly transmitted, red, mostly reflected. And these guys are where that thing couples to surface waves and sucks energy out of the reflected wave. It has to go somewhere. Yeah. The y-axis is still frequency. So this is 0 gigahertz. This was 350 gigahertz. Okay. Okay, so and what do these surface waves look like? I'm calling them surface waves because they're basically exponential decay outside of my effective medium film. So you can see all the different waves. This is at 40 gigahertz, 100 gigahertz, 190. You can see you just basically get more wiggles as you go higher and higher frequencies. But these are pure I could call them electric-based surface waves, where there's like a standing wave in here and exponential decay. You could count them bound states, but they're not magnetic based is the point. Okay, now I'm going to imagine I just turn on the magnetism. I've ignored it up till now. And I'm turning on the magnetism. I'm turning on damping. And now you see something very different. Again, frequency here, angle of incidence here. And look, there's this giant surface wave over here that it's coupled to and nothing over here. And so this is a very strong non-reciprocal effect, right? This dark blue, that basically means nothing is reflected. This bright red means nearly all of it is reflected. So it's quite substantial. And the most obvious thing is in this about 25 to 75 gigahertz range. But you can see there's stuff over here that is not over here. And even up near 300, there's also a difference. So to just quickly review, incident wave mostly transmitted, mostly reflected, and there was that, surface wave, non-reciprocal surface wave. What do you need for this? You need a permeability that has these off-diagonal components. Without that, you don't get that. And remember, we said that extends all the way up to about 300 gigahertz. Skipping all the calculations. Again, we do get localization that depends on whether you're going in the positive direction, plus K or minus K. You can localize at either the top surface or the bottom surface. So we do have those kinds of things still. And one thing that's nice about this is it's completely tunable in the sense that you can change the fraction that's magnetic and the fraction that's non-magnetic. You can change the spacing. So this nice thing is 40% is magnetic. And you can see we have a couple of different regions. Right here, a gigantic region of non-reciprocity, nothing over here, something on the other side. And even up here in the 250 to 300 range, you have substantial non-reciprocity. Okay, if you go down to only 1% is magnetic, nothing interesting happens. And if you go to 90% is magnetic, really looks pretty, but it's completely useless. Okay. But you got to admit, it looks cool. Okay, I want to do one more thing because I promised not to keep you for too long. We can also do something that is with a hyperbolic material. These have gotten very popular lately. What is a hyperbolic material? It is something where, let's say you have a diagonal, this is purely non-magnetic. You have a diagonal component of the permittivity tensor. And to be hyperbolic, one of these has to be negative, at least one, while the others are positive. If you plot this out, this gives a hyperbola in the omega and K space. Materials, you can do that with quartz. We're going to study transmission. Not that I can do anything about my internet being unstable. We're going to study transmission and not reflection. And what that means is we're not really doing non-reciprocal. And a non-reciprocal incident would be here, transmitted would be there, and then we would reverse the transmitted and incidents. We're doing something different. We're going to have incident coming in here versus incident coming in here, and just ask what's transmitted. So it's slightly different from non-reciprocal. So we're going to just transmit through a quartz slab, but it's a little complicated. Quartz has two different dielectric constants depending on whether you're on a principal axis or not. And we're going to rotate that with respect to the slab. We're going to, just example, 2.5 micron thick slab, and where this rotation is going to be 60 degrees. And here is, again, a nice complicated color map. This is basically the colors are showing you what is transmitted in this case. So, by the way, the frequencies here range from 13.5 to 18 terahertz. If you like wave numbers, 450 to 600. The color, and this is the angle of incidence again. So it's whether you're coming in from one side or the other. And you see a whole bunch of things. In this frequency range, it's very bright, everything is transmitted. In this frequency range, it's very dark, nothing is transmitted, no matter what angle you come in, right? That's remembered. But in this region here, this is a really weird region because over a lot of angles, nothing is transmitted, but in a small range of angles, there is a transmission. In fact, it's almost this angle right here. If you come in with this angle, you'll get transmission. And if you come in with any other angle, you mostly won't. Okay, so that is somewhat unusual. And you probably don't believe it. That would be my reaction. So we do have actually some different, we have an experiment in theory. Instead of the dramatic 2.5 microns, we couldn't get a quartz sliver that thin, but we could get one at 25 microns. The rotation of the crystal axis is only 5 degrees, but here's the theory. And again, it's the same thing. The color bar is how much is transmitted. Yellow is a lot transmitted. This is all the different frequencies. So here, basically everything is transmitted at this frequency independent of the incident angle. And here, nothing is transmitted independent of the incident angle. And at this spot here, only this one incident angle, right around maybe 7, 8 to 10 degrees, you get transmission just at that one angle. And you can see the experiment and theory line up really, really well. So despite the fact that you just don't want to believe this, me too, it does happen. And physics is nice in that way. It gives you all sorts of surprises that are contrary to your intuition because your intuition is bad. Okay, so to summarize, you have lots of different opportunities to massage high frequency electromagnetic waves. If you use antiferromagnets, you can get this non-reciprocal reflection somewhere in the 1 to 2 terahertz range, tunable with a magnetic field, right? I can turn it on and off. If you build yourself a nice layered structure like that, you can get non-reciprocal reflection. If you make that material a ferromagnetic metal like iron, you can first of all make it react in the high gigahertz range and low gigahertz range, and you can get non-reciprocal reflection as you saw in the range 0 to 300 gigahertz. And then finally, we can get this weird asymmetric transmission. I wrote 13 to 18 terahertz, but if you look at the quartz, if you look at their resonances in quartz throughout the infrared range, and you don't have to be limited to that small range. It happens to be the one we did the experiments for. So again, you can get this really, I think, quite spectacular, I don't want to say non-reciprocal, but asymmetric transmission with this system. And as always, nobody ever works in isolation anymore. You know, you feel like you should be Einstein and just come out with something brilliant, but no, it doesn't work that way. This has been a group that has on and off worked together over many years, and I'm showing you a little bit of all of that work. I want to point out Jair Macedo, who's originally from Brazil and now in Glasgow, because he did those spectacular experiments and a lot of the theory as well. But everybody contributed to this. And I was hoping to finish in 45 minutes, and I'm really close. So thank you very much. This is time for more questions. So thank you. Questions? Yeah, please.
So you showed reflection for the antiferromagnet, right?
Yes.
And then transmission for quartz.
Yes, that's correct.
Can you do the transmission experiment for then antiferromagnet, and would the resonance be also 1 to 2 terahertz?
Yes. It's a good question. You would certainly get some asymmetric transmission as well in the antiferromagnet because the absorption is different. The cool thing about the quartz was you don't need the magnetic field at all. The bad thing about quartz is you don't have any tunability, right? You're dependent on where the resonances sit. I kind of like your suggestion, though. Maybe I could combine the antiferromagnet and the quartz and make something really interesting. Okay. Any other questions? Yeah.
So do I understand right that effectively choose what's resonance by changing the thickness of it?
We
Or
could-
do you not change the position?
We're really changing. If you look, what we're changing is the angle at which it transmits or fails to transmit, right? Because all of the frequency seems to be lining up right around 550. Our parameters might have been slightly different for this, but you can see the interesting thing is right around 550. So it's good. Also, I will have to check and see if the frequencies are slightly different, but mostly we are changing the actual position where that transmission occurs. One of the other things, I didn't show this, but we instead of just doing one layer, we also did something with 2 layers, but with a rotation in one layer one way and a rotation in the other layer the other way. And what you get is something like this, but at slightly different frequencies. Yes, the one is like at this point you get one frequency, and over here you get another frequency. And so you could, in some sense, make a frequency demultiplexer, where if you come in with multiple frequencies, different frequencies will go in different directions. So there is a little bit of tunability, but not in the sense of I adjust an electric field and I can direct it differently. But I could get some tunability in a sense from my angle of rotation, and I could direct different frequencies differently. Yeah. I think that's a really good question, and we didn't investigate that. My suspicion is that you probably have to put too much strain on it to make a substantial enough difference. Haven't checked it out. One of the things you're working toward, one of the things I was intending to do, but I don't have the data for, which is liquid crystals, where you can orient stuff with an electric field. And liquid crystals also have this chance then to have, they have resonances in the infrared. They are asymmetric. So you could make a hyperbolic material and then orient it with an electric field. We didn't have the equipment to look for the resonances in that place. So I've kind of left it alone right now. If you have information on that, if any of you are liquid crystal people, nuts. I'd be happy to talk to you anyway, independently, but then I would have a real point and specific point to chat about. But I think a tunability that would be appropriate for this would be liquid crystals. That's my guess. I think that's the exciting area to go into next. And maybe we should keep that off the recording. Any other questions? Yes, please. The answer is, did we play around? Not very much. I mean, we made the thickness different. The same kinds of things happen, and it wasn't clear exactly what we would aim for as an optimal result. The other thing is, you don't want it too thick because you start absorbing more, right? And so in any electromagnetic kind of thing, you want as much transmission as you want, as big a difference, I should say, as possible. So we stayed with relatively thin films, but yes, I mean, clearly there are a lot of additional steps that you could do if you had a particular application in mind. Yeah, please. Yeah.
Is they're all the same sort of crystal orientation, so the permeability tensor between each one's the same.
That's correct. In essence, we're thinking of something that is polycrystalline, and the permeability is determined by the direction of the applied field. And that works pretty well, so that they're all effectively equivalent. Could you do anisotropy and make it more complicated? And maybe there would be some value in it. Yes. So imagine you had an anisotropy along the bars, and so some bars would be oriented with the magnetization this way, others this way. All of those things are possible and potentially interesting. Didn't investigate any of them, right? Good. Another really good question. You guys are ready to take off and do more exciting things. Yeah. It's all a variety, in a sense, the Faraday effect, where imagine you have a cylinder and you bring in an electromagnetic wave, which maybe is circularly polarized. And the one sense of polarization will go through with one frequency and one wave vector. The other sense, where it is circularly polarized, will go through and it will be different. And it is all based, again, on these off-diagonal components. Yes. Oh, sure, please. Yes.
So it means that you have one of the epsilon in the diagonal, which is negative.
That's correct.
And it's happening at a given frequency.
That's correct.
And this is this frequency range that you are able to see this.
This, yes.
So it's really an effect of all this
Hyperbolic.
negative side.
You need the negative sign.
in the sense that I was wondering if having just two different having an anisotropy is not enough.
I think that's, yeah, I think you need the negative sign, yeah. And again, to just add a little bit to that, the nice thing about the magnetic materials is, if you remember my very first mu picture, there is a region, or large region, where the permeability is negative. So magnetic materials, long before people invented the word hyperbolic, a lot of people in the magnetism community were doing effectively hyperbolic calculations with magnetic materials, because that's where all the good stuff happened, where the permeability was negative. Yes.
So it's like, I guess quartz is probably a great example of a material that does this hyperbolic.
Also cheap.
Have ideas for other that might have different ranges where this effect happens?
Again, my thought was liquid crystals, because it would be tunable. Liquid crystals typically have multiple resonances in the infrared, not as quartz does. Multiple, because they're basically molecular like vibrations in the infrared. So it has multiple resonances, but the resonance, liquid crystals are like, imagine a pencil, and the resonance for motion this way and the resonance for motion this way are different, which allows you to have one positive and one negative at a given frequency. So my material of choice, which would give you tunability, is, and everything else, is liquid crystals. Okay.